This is an appendix that explains how the rotational rate of galaxies is related to the amount of dark matter in the universe. So this is not going to be on the exam, and so if you want to skip this particular segment, feel free to do it, but I did want to show you some of the mathematics of it. So the idea for this is that you're going to have a galaxy, and most of the galaxy, the mass of the galaxy is concentrated in the galactic bulge. All right, now we're going to use concepts from Newtonian mechanics, so that if you go around in a circle, that's going to create centripetal force. So the centripetal force, when something is going around in a circle, is going to be given by mv squared divided by r. So let's say that you got a little particle located right out there. So the distance from here to here is going to be the letter r, and then this particle is going around and around at a certain speed v. So it has a mass m, has a speed v, you have to square it, divided by r, and then that's called the centripetal force. So the thing that's causing the centripetal force, the thing that's making it go in a circle, is the force of gravity. So that we could set this equal to big G, m, and then let's say this is the mass of the center of this thing here. So this is the mass of all of this material that is further in than this particle right here. So this mass is the same as this mass. This is the mass of all of this material that is inside the orbit of that object. And then divided by r squared. So if you simplify that, you get the first equation. V is equal to the square root of big G, and then this would be the mass that is inside right here, and then divided by r. So that's your equation. So that's that first one there. However, the mass is not uniform inside of here, so that instead of mass, we could write it in terms of its density. So density is equal to mass divided by volume, and then the volume could be written in terms of the radius. So when you take this m right here and you substitute this m right here, so you put the two equations together, then you get that it's going to be, turns out when you simplify it, the square root of G times the density and then times r. So the point is that as you increase the r, so you start here, and as you get further out in a galaxy, the rotational rate of that galaxy ought to increase. As r increases, so does the speed of the rotation. And so that's the reason why on the graph, which is up above it, you notice that the graph starts to go up. So this is the distance r going sideways, and then this is the velocity going up and down. So the further you get out in the galaxy, the speed initially increases. Okay, now let's look at part C. So in region number C, we're looking out here. So in this region out here, you have most of your mass is now in this part, and there isn't so much mass out here. And so what we find is that the speed begins to decrease. So you should know this, because if you look at the speed of Mercury as it goes around the sun, it goes very fast. But by the time you get out to Earth, it's going slower. So because all of this mass is concentrated towards the center of the galaxy, the further out you get from the galaxy, the speed starts to decrease. So if we connect these two places right here, you notice it's kind of flat. All right, when we actually measure the rotational rate of galaxies, what we find is it does go up like this, but instead of going down like that, it stays like this. It continues to flatline. And then way, way, way out there, it finally starts to go down like that. And so what that means is there has to be more mass in the universe than what is used in order to calculate these different parts of the graph. And so that missing mass is the dark matter that is in the galaxies. Okay, just want to show you another appendix here. I kept talking about the 11 fundamental constants of the universe. And if you recall, we said that, for example, big G was one of those fundamental constants. And then another fundamental constant was the speed of light. So there they are. So those are the fundamental constants that control the universe. This really bothers astronomers because in the same way that they'd like to have one particle in the universe, they'd like to have one force that controls everything, and they'd like to have one fundamental constant. Why are there 11 of them? So there are 11 fundamental constants. And if you take any of those 11 fundamental constants and you change the number by just a little bit, the universe falls apart. So all 11 of those constants have to be tuned to specific numbers, otherwise the universe doesn't work. And so a lot of people say, why? Why do you have to have 11 of them? Well, so here is another way of thinking about the fundamental constants that rule the universe. So if you want to take a look at that, you should recognize a lot of those names now. So you should recognize the W boson, the Z boson, the Higgs boson. You should know what electromagnetism is. You should know what the strong coupling force is. So that's the thing that causes the strong nuclear force. And now this is really wild. Somebody had a lot of time on their hands because they took various fundamental constants and combined them. And it turns out that if you take the square root of the Planck's constant times the gravitational constant divided by the speed of light cubed, you get the dimensions of meters. And so this would be the ultimate metric unit. So this, even if you were an alien in some other part of the galaxy, you would still have those 11 fundamental constants. And if you were to combine those fundamental constants, you would get the same exact number, 1.62 times 10 to the negative 35th meters. Where have you heard that word, negative 35 meters, before? That was the size of a superstring. That's where they got the number from. The smallest possible distance in the metric system is that number there. Then you also can combine the constants together to get Planck mass. So this would be a fundamental metric unit of mass in terms of kilograms. You also have Planck time, 10 to the negative 44 seconds. Keep that number in mind when we talk about the Big Bang and the beginning of the universe. You also have Planck temperature. So do you remember that when we talked about what was the temperature necessary in order to get or to get TOE, the theory of everything? That's where that number comes from. And then you have also Planck charge and the Planck mole. So again, somebody had a lot of time on their hands when they came up with this stuff. Okay, let's take a final break. And when we come back, we are going to take a quiz over what you've just learned.